Assalamualaikum and a very good day to all of you. Okay, we continue our recorded lecture. Uh, Today we will look at stresses in the vessel. Okay, so for those that very new with this channel, I'm Shikin Aziz. I'm preparing this recorded lecture for my student, undergraduate student of process and food engineering. All right. And the topic is actually under subject of process equipment design, EPF 4801. Right. Okay. As been explained in previous lecture, all right. Uh, you should know by now that pressure vessels are subjected to several loads. Okay, in addition to direct pressure, and you must design the pressure vessel to withstand the worst combination of loading without failure. All right. So, in order for us to find the right thickness, okay, uh, from the calculation, all right, there is the stress from all loads that we determine will ensure the maximum allowable stress intensity. All right, and then the maximum allowable stress is intensity should not be exceed at any point. All right, so here is the list of main sources that need to consider, right? So we have covered the direct design pressure, including the static head of unit, maximum weight of vessel and content, maximum weight and content, wind loads, earthquake, and external loads. All right. Detail of this has been explained in previous lecture. So now let's look on the primary stresses that may arise from those loads that I showed you just now. All right. So the stresses will include the longitudinal stress, and this can be calculated by using this equation, and circumferential stress. All right, circumferential stress, or other name of it is hoop stress. Okay, so we need the inlet inside diameter, the thickness of the plate, all right, and the pressure. Then let's look on next, which is a direct stress. Okay, so the direct stress is due to the weight of the vessels and its content. Okay, to the weight of the vessel and its contents plus attachments. Okay, and then this stress can be positive or negative. All right, so the positive stress is actually showing a tensile stress, while for negative stress it's represent a compressive stress. All right, so compressive stress is normally on the top, okay, on the top of the plane of the vessels. All right, vessel support, while below the vessel support normally is a tensile stress acts on it. All right, then for the dead weight stress will normally be significant, okay, compared to magnitude of other stress for the tall vessels. And here Wz is a total weight which supported by the vessel wall at the plane considered. And then bending stresses, okay, bending stresses may result from the bending moments to which the vessel subjected to. Bending moments will be caused by wind loads on tall self-supported vessels, earthquake loads, or seismic on tall vessels. The eccentric loads, okay, the eccentric load, okay, due to the dead weight and wind loads on piping and equipment that is attached to the vessel, but offset from the vessel center line. Then horizontal vessels with feather support from the deposition of dead weight load. All right. The bending stress, it could be compressive or tensile, and this is depending on the location. This given by this equation, where M is a total bending moment, while the second moment at the plane of bending, all right, IV, is given by this expression. All right, is given by this expression, and uh, this is actually second moment of area of the vessel, about the plane of bending. Okay, let's look next. Stress is, we could name it as torsional torsional shear stresses. Okay, torsional shear stresses. All right. So for torsional shear stresses, uh, which will be caused by loads offset from the vessel axis. All right, and these loads will normally be small. All right, and need not to be considered in preliminary vessel designs. All right, you need to take note this. All right, and the expression is given by this. You can use this expression to calculate torsional shear stresses. And there is a second polar moment area, which is represented by this equation. All right, sorry for that. Okay. Okay. Then after we have done this, we can calculate the principal stress. So there are three components of principal stress: stress 1, stress 2, and stress 3. Uh, the 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 sigma z here is expression for total longitudinal stress. All right, and sigma w here, okay, it can be counted as positive if tension, while negative is compressive. All right, and then the what is it, for the tau is not included here. Right, for the torsional, okay, it's not included in here is because it's normally it's not significant. And then the third principal stress, this one, the third principal stress, which is in radial direction, will usually be negligible for thin wall vessel. All right, but for approximation, you can use this expression. All right. Then let's look on the allowable stress intensity. Okay. So the expression of this will depend on the theory of failure that you adopted in your design method. All right. And the maximum shear theory is normally used for for pressure vessel design. Then by using the criterion of the maximum stress intensity at any point taken for design purposes, so uh, the greatest value from here, all right, from this will be used as the maximum stress intensity. And then must make sure the wall thickness is enough to provide the maximum stress intensity. Wall thickness uh, does not exceed the maximum allowable stress of the construction material. Alright. Okay, so your vessel wall thickness must be sufficient, okay, to ensure the maximum stress intensity does not exceed the maximum allowable stress, okay, or other name for it is nominal design strength. Then let's look on next compressive stress and elastic stability. All right. So when the resultant axial stress uh, become compressive, okay, due to combined loading. So the vessel may fail under this condition actually, due to the elastic instability, or other name for it is buckling. All right. So for this, there is a precaution in vessel design where uh, maximum value of the resultant axial stress must exceed the critical value of buckling occurrence. All right. So local buckling will normally occur at a stress lower than the that required to uh, buckle the complete vessel. All right, and due to this, uh, a column design must be checked. All right, must be checked to ensure that the maximum value of the resultant axial stress does not exceed the critical, okay, the maximum value of the resultant stress, the resultant axial stress does not exceed the critical value of the buckling, okay, where it will occur. So basically class for this, all right, we need to calculate the critical value for the buckling occurrence. Then we need to compare with the maximum value of the resultant axial stress. Okay, so the how to calculate that? We can use this equation for a curved plate. All right. So this is critical buckling stress. Okay. So what we need is curvature radius, Young modulus, outside diameter, Poisson's ratio, and thickness of plate or shell. Okay. But there are several expression here. The final expression is this one. After it has been uh, simplified. Okay, so here how it's been simplified by first, by applying Poisson ratio of 0.3, and then and finally it will the expression is simplified by applying safety factor. Okay, by applying safety factor. So this is some typo, right? Okay, by applying a safety factor. So this final equation can be used to predict the maximum allowable compressive stress to avoid failure by buckling. All right. So while a large safety factor is needed, is due to because some experimental work has shown that cylindrical vessels will buckle at values well below that given by equation, this previous equation, right? This previous equation by this one. So due to that, the final equation here has been incorporate a safety factor, right? Which is safe to be used. So when we calculate this, we must make sure that the maximum compressive stress in a vessel should not exceed the equation of this. Okay, should not exceed the equation of this, or the maximum compressive stress in vessel should be less than maximum allowable design stress of the material. Alright. So for detailed design of this can be obtained from ASME BPV code section 8. Right. Then stiffening. Okay. You have heard this term stiffening when I explain in the vessel support for skirts design support. All right. So basically, the stiffening ring or longitudinal strips are included in the vessel design to provide resistance to failure by buckling. So if let's say your design have 6 stiffening rings, there are special equation for this. All right, and then you need to refer a standard that have given that provides a method to calculate buckling for the design with stiffening rings. All right. So now, so sorry, it's basically to calculate the buckling at the stiffening, at the stiffening ring. Now, loading. Okay, for stiffened vessel. Okay, stiffened vessel. And then all loads which are considered in the vessel design. Okay. Oops. Sorry, let me correct myself. So this one, you can find a standard to find a calculation for buckling. Okay, stress due to buckling for stiffened vessels. And then for loading, right, the load to which a vessel may be subjected will not all occur at the same time. For example, uh, the maximum wind load will not occur simultaneously with a major earthquake. All right. So the vessel actually you must design by taking into consideration the combination of the load. For example, during dismantling or erection of the vessel, or with the vessel erected or dismantling but not operating. Then third, during hydraulic pressure test, and last one is during normal operations. Okay, so that's it for now. That's it for now. All the expression involved for calculating the primary stresses and principal stresses. Right. So we shall meet again for the next lecture, recorded lecture. Alright, so bye. Assalamualaikum.